Good afternoon to all of you. Good afternoon, Jamo. I hope you all can hear me and see my screen. Hello, Namishka. Welcome to a surprise early Saturday afternoon lecture. Otherwise, our lecture used to be late afternoon, which was a fairly a boring time to take a lecture. I hope, I think all of you will agree with that. So let's start with this 17th lectures on acoustics. Going ahead, in this class I'm going to talk about acoustic impedance. Uh, we need to understand this concept before we go ahead. You will not find it in the current chapter that we are doing in the reference book. You will have to go back to chapter 4. It has been introduced as one small topic in chapter 4. You can read it from there and then come back. We need this to take our discussions forward. Remember, last class we were talking about clarinet and other woodwind instruments. So acoustics impedance is the first thing. Impact of open tone holes. In case of clarinet, we are going to talk about. We are going to talk about the register and register holes. And finally, we are going to talk about another instrument apart from clarinet, another woodwind instrument, which is a modification on clarinet, and that is saxophone. So, going ahead, what is acoustics impedance? Typically, the acoustics impedance is defined as it's a mathematical calculation. The sound pressure divided by the volume velocity U. P is the sound pressure and this is the volume velocity. Volume velocity is nothing but the volume of air flowing through a specified area per unit time. So if you figure out the volume velocity, it is a volume divided by time and pressure is force upon area. So if you do this calculation, it becomes rho V by A, the cross sectional area. So in this case, you will find that the Z varies inversely with cross-sectional area A. What it means? What it means is if you have a instrument where the cross-sectional area is large, it will offer a small impedance and vice versa. With a smaller area, it will offer a large impedance. The situation becomes more complicated and creative when the in case of saxophone that we are going to talk at the end, where we will see that the cone diameter varies continuously. Okay, so going ahead, the significance is very important. High impedance means a small acoustic flow generates or requires a large pressure. Look at the formula once again. Z is equal to P by U. U is the volume flow. If you want large Z, I mean, if the acoustics impedance is large, I mean, think about it in this way. U is the volume flow. Volume flow means hard you how hard a person blows into the instrument. Now, if you have to blow hard to generate a given pressure, then impedance would be less. And if you blow very softly and the pressure generated is large, then your impedance is high. So that's how it is. So high Z means a small acoustic flow generates a large pressure. So it is good for driving a reed or lips. Such instruments are easier to play. That means you blow into them very softly and they generate large pressure towards the outside. So that is the case of high Z. A small z means a large acoustic flow generates a small pressure. So that is good for driving an air jet in and out of the flute blowhole. So normally all flutes require typical Indian flute and other kind of flutes require a huge amount of blowing. They are not easy instrument to play. Now, again in an instrument, the Z varies as I said. It depends on largely on the design of the instrument and it varies with frequency as well. So depending on which hole you are keeping closed, which hole you are opening, which frequency you are playing the instrument at, the impedance will keep varying. So that becomes a very significant part of mastering a woodwind instrument. It decides the stability of the note. So for example, if you're playing a particular note and if the impedance changes during the play, then you will face difficulty in the note. Or for example, if you are blowing in the embouchure of an instrument with a certain pressure, but suppose you get tired and you drop the pressure, then the impedance will change and again the note will change. So one has to be very careful. For woodwind instrument, it is a function of physical property of the instrument alone, and that's the relieving part. That impedance is only the function of the design of the instruments and not the performance of the person. So for a given instrument, it will not depends on the performer's ability to handle the instrument. It will depend only on the instrument. And also it is a spectrum. It varies with frequency as I have already talked. So how does the acoustic impedance look like? Of course, it decides the interaction between the player's lip, reed, or the air jet from the mouth. So how fast you blow into an instrument, that will decided by its impedance, input impedance to be called specifically. Now here are the two graphs which on the y-axis plot input impedance and on the x-axis plot frequency. We focus on the first one. And what it shows is the impedance changes with the frequency and it goes like in an harmonic manner. So for certain frequencies you will find that the impedance is very less. You can see these are the points where impedance is very less. Where the impedance is very less, those frequencies are created very easily in the instrument, and those frequencies, those resonant frequencies will sound loud. At other places, the impedance gets very high and those frequencies are actually suppressed. Those standing waves or standing waves at this frequency or this frequency or this frequency will not be generated in the pipe. Now, how does a clarinet differs? In a very interesting way. If you have a clarinet with all the holes open and if you drive it with uh, if you blow into it with sufficient constant pressure, you will find that the impedance again varies with frequency. So certain frequencies impedance is very low, those are very strongly set, certain frequencies are rejected. But interestingly, you will find that for a clarinet, there seems to be, and I'm not just talking about a clarinet, any pipe which has a tone hole lattice, which has a set of tone holes, even for a flute. So what happens is that the higher frequencies are kind of there exists a higher cutoff frequency above which the fluctuations in these impedance or these impedance peaks are muted completely. So very high frequencies, they just go through the they just sail through the pipe very without any hindrance. But at low frequencies you will get lots of variations. So there seems to be existing a cutoff frequency for a given pipe with the hole. But if the pipe does not have the holes, then these variations continue. So that is a very important thing. And this cutoff frequency has a formula. And that formula is actually given by this, where the various parameters are here. Now, these parameters are nothing but A is the radius of the bore, B is the radius of the tone hole, S is the tone hole spacing, 2S, T is the tone hole height, etc. So depends on how you drill the tone holes in the pipe, that will decide the cutoff frequency. So how big the tone holes are, what is the separation between the tone holes, etc., etc. These will determine that what will be the cutoff frequency, and which frequency will be reflected back, which frequencies will be transmitted. Now just remember the basic physics also. These are all numerical results, but the basic physics is very simple, that if you increase the frequency, the wavelength decreases. The moment the wavelength becomes smaller than the diameter of the bore, sorry, diameter of the tone hole, then the diffraction sets in at the tone hole, and then the air will start leaking, rather air pressure will start leaking through the tone holes, and that reduces the chances of stationary wave formation inside the tube because the pressure leaks out. More high the frequency, the tone holes become much bigger and the wavelength become much smaller, and most of the sound energy is radiated out, and standing wave formation hardly take place inside the tube. So if you have an access to a tube, this can be a very excellent project to work, figuring out these impedance curves, the previous these drawings. So all you can do is take a plastic tube, long plastic tube, long means maybe 2 feet or something, between 1 and 2 feet. At one end you can drive a speaker. You will have to calculate first of all that what are the range of frequencies, what is the fundamental, what is second, third up to 10th harmonic. Figure out that range of frequency. Then on one end you have to keep a speaker, mobile speaker, small speaker, and feed that sound to the tube. On the other hand, you can keep the microphone of an hands-free cable and attach that to another mobile's decibel level sensor or real-time analyzer RTA, that they will give you the sound frequency which is sensed. They will also give you the amplitude which is sensed. So you can have a frequency which is driving the tube at one side, and you will have the sensed amplitude on the other side, and you will find that as you change the driving frequency, your amplitude will fluctuate. It will go up, down. And from that, you can figure out the resonances and then use suitable formula to calculate impedances. So that's a wonderful project to work. In fact, you can drill some holes in the plastic pipe at regular intervals and then again redo the experiment to see if there is any difference between this and this. So going ahead with that suggestion, how the reed vibrations affect the sound which is being generated. So that they do affect, and they do affect quite a bit. Now if you are blowing into the clarinet softly, then in that case what you get is a very little vibrations in the reed, and the vibrations are mostly sinusoidal. So most of the sound that is generated is sinusoidal in nature. So that is a very straightforward. However, if you blow hard, then the sinusoidal structure gets distorted. Some sort of clipping happens. As the clipping happens, you know that it's no longer sinusoidal. Then the Fourier analysis tells us that you will have some harmonic structure. It is no longer a pure frequency, but it's now a harmonic. So harmonic structure sets in. If you blow it even harder, the amplitude gets larger, but distortion becomes stronger. So you will get more or less a square wave or square pulse kind of situation, and you will get large number of odd harmonics. So that's how even how hard you blow into a clarinet will decide how much or what kind of frequency spectrum you are generating. Now register and register holes. Registers are, we sometimes talk in terms that the instrument is playing in one register or instrument is playing in another register. Now you all know that we have number of holes drilled on woodwind instrument like clarinet, saxophone, flute, shehnai, etc. Number of holes which are drilled to give a particular frequency or pitch of the sound. However, there is one more hole which is called register hole, which is very wisely drilled in a way that you can, from the same instrument you can create another scale of music. That means all the 6 or 7 holes, whatever music they generate, that entire scale shifts to a different level, and that is the property or that is the function of a register hole. So a tiny hole is drilled, say at about 1/3 distance from the reed end of the pipe. So in case of a clarinet, there is a small hole here which could be opened or closed by, in clarinet it is done by using either by finger if you want to do it a quick closing opening, but it can also be done by a plastic cap or a rubber cap. Suppose if it is closed, then an antinode is created here, pressure antinode, and a pressure node is created here. But suppose if you open it, then what happens is the air from this open hole leaks to the surrounding and the pressure drops at this point. So a pressure node is created automatically at this point. So what is happening is, in opening of this from closing, if you have this thing, just to tell you, this was playing in the fundamental frequency, then the wavelength will drop and the frequency will increase. It will now be playing into the third harmonic. So just by opening or closing, you can shift the entire scale by 2 harmonics up. So if it was playing in first harmonic, it will switch to third harmonic. So that's how the scale changing is achieved in a typical this kind of instrument. This is, remember, hole is drilled at 1/3 of the distance from the reed end. I can drill a hole at 1/5 of the length from the reed end, and if you do that, it will lead it to, now remember the third harmonic does not fall here, so it will lead it to the fifth harmonic. So I can open or close this register. There should be a correction. This should be fifth. So if I open or close this register, then it should play in the fifth harmonic. So just by pressing or opening a key, you can change the entire scale for all the instrument, for all the parts to a new scale. So that's a very interesting feature most of the woodwind instruments possess. Saxophone is a very important, very popular instrument, probably because of ease of its playing and the kind of sound it generates. I bet all of you have seen it. I had shown one image in the last class. We will end the lecture by a short video on the saxophone. It is a conical bore single reed instrument. Remember that. It has a conical bore. So I'll show you the instrument. It will be very narrow at one end and then slowly the width of the instrument goes on increasing and flares out. Unlike in a clarinet where most of the pipe is cylindrical, only at the end there is a bell-shaped opening. But it is the pipe is cylindrical. Most of the sound producing happens in a cylindrical manner. But in a saxophone, it is a conical bore. It was invented by 1846 by Adolphe Sax. That's why the name. It's popular with jazz bands. I'm sure many of you must have seen it, must have heard it. Those who are familiar or those who listen to Western music with interest, they must have come across it. Bollywood hardly use it, although there are some songs where they have used it in a very interesting way. It has a very large bore diameter. It has a large volume of air to be pushed, and because it is conical, the input impedance, its input towards the input and cross sectional area is less, so input impedance is high. You blow into it softly and it generates lot of air pressure later on. The it has a louder sound than other woodwind instruments. It's fairly a loud instrument. So you don't require, if you are particularly playing it in a closed halls, then you don't require an amplifier. Yes, if you are playing in a stadium like situation, you might need an amplifier. It has both odd and even harmonics. Remember, we had discussed in the last class, if the bore diameter increases or conical, then it has both odd and even harmonics. And the registers are an octave apart. Think over it. Like you open and close, and all the frequencies get doubled if you open the register. So it's just switches. The entire instrument switches into an switches by an octave in its scale when you open or close the register holes. Look at the structure. Here is the player. You can see that this is very narrow at this end, but as it goes, the width of the pipe increases linearly with the distance from this end. Of course, it has been bent, so just imagine that these bends are not there and it's a straight pipe. So if you imagine this as a straight pipe, then you will find that the width is increasing and eventually becoming very broad over here. So it's increasing gradually in a cylindrical, no, in a conical manner rather. It's a cone. Okay, the register keys will be placed somewhere here, the playing tone hole keys somewhere here. It's relatively a heavier instrument than a clarinet or a flute, so the player requires a strap band in the neck to give the support. That's very important, although some prefer not to use the strap band as well. But if you have to, I'm sure if you have to play it for a long time, then the strap band is needed. So let me see, or let us see how this guy plays for us. So I don't know, I can just wait and wait for him to play. Yeah. Now this was playing in a very higher pitch. Uh, as I said, the Bollywood have hardly used this instrument in its music. Few songs are still there. One of my favorite piece of jazz from Bollywood music is from a movie from 1960s. Check it out. Here the instrument has been played at a much lower pitch than it was in the previous example. So yeah, you can figure out more about these videos and these songs from YouTube. I think some links will come in the descriptions as well. We can stop this lecture here today. Thank you. We will continue with the next lecture again about the woodwind instrument. In fact, the next lecture will be the last lecture on the woodwind instruments, where we will take some problems as well. Thank you once again.